Okay, so if we are ready, I can continue. I hope you all had a nice break. Are there any questions from before? So once again, yes,
No,
was that a question? So we saw how a neural network works, and we define artificial intelligence, which is important these days when these three terms are used interchangeably. And we also discuss about other things that go beyond just the technical or computer science part of artificial intelligence. So in the next few slides, I just want to explain how we went from feed-forward neural networks all the way to transformers. So feed-forward neural networks were invented in the 40s, and they were very good at first, but then they had several problems. The vanishing gradient problem, for example, or um, overfitting, like the ones that we talked about yesterday. Um, and the biggest problem was that they were still tied to the bag of words model. So yesterday we talked about this bag of words is like you try to come up with all sort of conditional probabilities of a document to belong to a class given the kind of words that it contains, and then also the frequency of these words. But then there's so much that you can do just by counting how many times a word appears in a document, right? So the one thing that we couldn't do for the longest time was to encode context. So it's not just about a bag of words, but really having context, contextual information. So what is contextual information? In this case, just the neighbors, the neighboring words. And that's something that convolutional neural network could do pretty well initially. These they were actually proposed in the context of computer vision. So when you look at this GIF here, GIF on the left, it's the original convolutional neural network algorithm applied to an image. So image processing in the past has the same problem of text processing. People were trying to categorize images based on the singular pixels, but then especially with image, you understand how that's a very limited approach. So Mikolov had this great idea of using someone that actually Jan LeCun invented back in the 80s, which was let's define each pixel not just by the pixel itself is in a bag of word model, but in a continuous bag of word model by also encoding the contextual information of that pixel. So you see here in the green part of the image, we are trying to encode a representation of each pixel based on what? Based on the neighbors, the nearest neighbors of that pixel in the original image. So I have this sort of sliding window, which in this case is of size 1 pixel, because I look at the pixel itself plus each of the neighboring pixels, and then try to encode this information how, again, in a matrix, in a numerical form, as I slide through the image. So this is something that was initially proposed in the context of computer vision image processing, and it worked very well. And then it was then transferred to text processing. So this was a big revolution, actually. This is what started the deep learning revolution. It was nothing new because convolutional neural networks existed for 30 years, but then this needed some computational power and also, most importantly, a lot of data. And back then in the 80s, we didn't have so much data to be able to even think of training a convolutional neural network. So here, once again, I don't want to bother you with technicalities of the convolutional neural network, but it's once again a mathematical operation, a convolution operation, which basically compresses information and encodes information of the contextual data that you have. So, for example, all these images that you see of convolutional neural networks that compress data from a layer to another, they're mostly just max pool operations. So what is a max pool operation? Simply dividing my set of data into different units, and then for each of them, I just take the maximum. So here is a simple example of 2 by 2 max pool. And this, of course, is made in much bigger dimensions, but this is mostly um, the methodology. I try to, as I slide through an image or a document, I also encode, you could say, I also count the occurrences of their neighbors, which in a word would be the word that comes before and the word that comes after the target word. But then, of course, as I do all these, I need to compress this information as I go through the document or the image, and that's why I need to do these max pooling operations. But nonetheless, this turned out to be very useful in image processing, because then for the first time we could really encode salience in images. Thanks to this approach that will look at the contextual information, CV algorithms became very powerful at recognizing specific areas in an image and recognize objects also in an image, or faces and whatnot. Something that we could never do before without this kind of contextual encoding. And so this, as I already mentioned, has been transferred later on to word embedding. So the good thing about word embeddings, first of all, is that it's encoding context. So we're not talking about bag of words anymore, but continuous bag of words. Each word is not only represented or encoded as the word itself, but also what with the word or words that come before and after that word. So this is good for having more contextual information, but also because once I set on a specific set of embeddings, like word2vec, then this is very good because, for example, before, to represent the item burger, we had to come up with some sort of encoding, and it was clearly just made up. We had 3 foods, and so we created this 0, 1, 0 vector to represent burger, but that was quite a random choice. If I use word embeddings, first of all, I have more contextual and informative information. And second of all, when I decide to use a specific set of embeddings, the same word embeddings that I have for burger will also be used by someone else at the other side of the world who is using the same set of embeddings. So it's also good for standardization in a sense. So how do they work is similar to what we've seen just now for encoding of context in an image. And here you have an example of how it can be used also for word sense disambiguation. We'll talk about WSD later in lecture 3, but here the point is that before, when we were using the bag of words model, we were just building this co-occurrence matrix in which we were counting basically how many times each word appear in each document, but here we are calculating actually some conditional probabilities. We have this sliding window, once again, in this example is a size 2 sliding window. As I go through the sentences, I encode the probability of this word also based on the conditional probability of other words to appear before or after the target word. So it's just a trick. We didn't know for the longest time, we didn't know how to encode context. But now, thanks to convolutional neural networks that look at these, at words that become that come before and after the target word, we can finally encode context. And the results that people initially got were even more exciting than expected, because this was mostly like a probability based or syntactic based approach, because I'm just blindly looking at what comes before and after the word on a fixed sized window. But actually, what they obtained with the first few vectors was that actually also some semantics supposedly were captured. And the famous example of this is that if you took the word embedding representing the concept of king and you subtracted the word embeddings of man plus the word embeddings of woman, you would get a resulting word embedding that was similar, very similar to the concept of, to the word embeddings representing queen. So this was the claim of initially for the fact that word embeddings could also encode some semantics. Now, that's not exactly true, because then once again, we're just playing with numbers and probabilities, but it was nonetheless very cool to see this. This was something that could never be done with the bag of words model. So in the next few slides, I'm just going to go through a short history of word embeddings. The very first one was the one by Google, Word2Vec, that was based either on the continuous bag of word or skipgram, which are two mirrored examples of how a word embedding model can be trained. Later on came GloVe, and this was also taking into account, because the one problem with Word2Vec is that, for example, the frequency was completely left out, and that's a mistake actually. So the FIDF was mostly based on word concurrence frequency, and then when we first built Word2Vec, we thought, okay, frequency is not good, let's forget about it. But then GloVe reinstated some of that, and it turned out to be actually useful for at least for some data sets. Fast text by Facebook was also very interesting, because then every word embedding in the previous embeddings, you could also have that. For example, words like trust, trusted, and trust would have completely different word embeddings. Why? Because of how the pre-training was done, depending on where and how these words would appear in the training data set. So FastText was trying to get away from this by handle the morphology of words, so that also words like trust, trusted, and trust, and so on would have similar embeddings. Elmo was also very powerful back then, because it was also handling disambiguation. So one problem with previous word embeddings is that each word had a static word embedding. For Elmo, the word embeddings became dynamic. So every word, or at least a word that had multiple senses, would have a different embedding based on the context, based on the sense that was in which the word was used in a given context. And last but not least, we had BERT, which is based on transformers. The T of BERT is transformer. What is a transformer? We'll see it later, but BERT is what was been also very much used for the past decade, and there were so many different options, so many different alternatives to BERT, including Roberta. Roberta is maybe the one that is most used for NLP tasks and still very much utilized today. But then, yeah, we haven't seen what a transformer is, and that's because we haven't talked about recurrent neural networks yet. Let's briefly talk about these two using the example that we used before of the cook and the food. So it's called recurrent because it has this sort of feedback loop. This, once again, is nothing new, because even with feed-forward neural networks, we had backpropagation back in the days. But still, this is important. Why? It's a sort of forget gate that recurrent neural networks were using to forget the contextual information that was not too relevant. In fact, when you do the biggest problem of a convolutional neural network is that as you go through the sentence or the image, there's a lot of context to be encoded. And even with all those max pool operations, it can still be a bit confusing for the neural network because then you're encoding all this context, but sometimes some of the context is meaningless, right? So we needed some sort of forget mechanism that could get rid of the not so relevant context. And that's why recurrent neural networks came about, like LSTM, for example, was very much the state of the art in natural language processing for many years until recently. So we can take back the example from before and make it a bit more complex. In this case, we have a sequence. So that's what recurrent neural networks are good at, modeling sequences. So let's say that my chef friend is cooking this kind of foods in this sequence. So I can have a new network that does this. So once again, it's just a multiplication of matrices. So if I have pizza, I get burger. If I multiply the burger vector for that matrix, I get sushi. And same with sushi, then the loop restarts from pizza. This can also be represented as a graph, as we've seen before. With recurrent neural networks, I have this feedback loop. So this is good for adding a new condition. So now we have this new condition that if it's sunny, then this friend is cooking the same food as yesterday, maybe because he went out to have fun and used the leftover from the previous day. If it's raining, then go to the next dish. So here we have to start doing a bit more complex operations, but the takeaway of this is that we're still just doing multiplication of matrices. So I represent the food in these two halves. Why? Because I want to know what to do, the current food and the next one. But the way it works is the same as before. I'm multiplying this new matrix for the vector that represents pizza, and then I get 100010, which means that if it's the same for the same day, I still cook pizza. Otherwise, I cook burgers. I do the same for the rest so that I know what are the possible actions that I can take. And then I have to model also the weather. Weather, I do something similar so that I know how to model the sequence of weather that converts from sunny to rainy and vice versa. Then I do an add operation to put together the objects of my action in the operating environment plus the condition, the weather, and this is how I can then answer questions like this. Yesterday, my flatmate cooked pizza. Today is raining. What will he cook today? So I have to add up these two matrices that I've just calculated, and then I get this 100121. I need to merge these two together to get the final answer, because then the final answer is what is a type of food, which is a three-dimensional vector as we defined previously. So I need to do some nonlinear operations to convert these to something that I know. I can, for example, do -1 everywhere. And then I get, when I merge these two informations together, I get my 010. So this is a very simplistic example. A recurrent neural network is much more complex than this, but still it's important to understand that I'm doing some kind of operations among matrices that are not very different from before. I'm just using some tricks to add some conditions. And this is why recurrent neural networks like LSTM and GRU were very popular for the longest time. But they were also suffering from some problem, like the vanishing gradient problem. They were also not perfect at remembering the important context in case of very long sentences or very long paragraphs. But most importantly, because of the way they work, the fact that they worked in sequence, they were hard to parallelize. So if I had to look at different types of attention, or if I had to process the same document from a different point of view, I still had to go on a sequence. I still had to process the document from the first word or the first letter to the last. And this is a big problem that transformers don't have. So as we'll see later, transformers actually are the next evolution of recurrent neural networks, but it's not like they're a huge technological advancement. Actually, the biggest discovery about the biggest novelty associated with transformers is simply that they can be parallelized. So what does it mean? It means that I can throw more hardware, more computational power at it, and the accuracy will increase. Before we get there, we have to talk about the sequence-to-sequence model. So sequence-to-sequence model is also very interesting because in a way is also kind of cognitive inspired. So we have, it's like playing the game of Pictionary, where you have to read a piece of paper and then without telling your friends, you have to draw what you read and your friends have to guess. So you, in this case, would be the encoder, the one that has to encode the meaning, the information of what you read, in this case, Polish. Then you present this compressed or hidden state to your friend, and your friend has to decode the meaning into the same word that you read without communicating the same word. Now, in the game of Pictionary, it's just a game, but why can this be useful? Because then when we want to do, for example, machine translation or any kind of sequencing task, this can be very useful. So the reason why this was interesting and also the state of the art for a very long time is that it's also as I said, quite cognitive inspired. As it's a happening. What's happening here? It's a bit what I mentioned before when we said that when I have to translate from a language to another, I read the sentence, I encode the meaning in my brain, and then I decode in the target language. So in this example, we have an example in Spanish, and it gets translated into English. How does that happen? In the past, I would have maybe tried to translate word by word, and that's a mistake because, as you know, you cannot do literal translation. It won't be as good as a proper translation from a language to another. So instead, I represent these three words using some sort of convolution, some sort of continuous bag of words into this compressed hidden state, and then I pass this to my decoder, who instead has another kind of dictionary to translate the same meaning into a new language, into English, the target language. So this sequence to sequence or encoder decoder model, you could see it as a sort of Rosetta Stone that helps me translate, encode and decode meaning, and in this specific case, from a language to another. But this can also be applied to many other tasks. Machine translation is maybe the best task to explain why and how this works. So once again, I'm inserting into the encoder different bits, bit by bit. Look, so in this case, word by word. And then what I'm doing inside the encoder is that I'm modeling the context once again. It's not like I'm just doing a translation word by word, but I look at as I go through the sentence. I have once again my sliding window, and I can also have more stack more encoders, more recurrent neural networks inside to do this as I go through the sentence. And then once I build the final hidden state that I pass to the decoder, I do the same at the decoding phase to translate the sentence into the target language. So after this, people started to use masking to kind of predict which word would appear in a specific position in a sentence called mask. And this was the stepping point to then go into sequence generation. And this is where then generative AI came about, because then once I'm able to do this, to predict what kind of word comes here in the mask, then it means that I can also do it word by word in a sequence and just predict the next word. And that's how we went from modeling sequences to prompting to generation, where I can model any sequence of words, pixel, and now even speech and video. And this has been the holy grail for a while, because then search engines and many other applications always needed something like this, something that could correctly predict the next word based on the context. But once again, is what's happening inside these transformers is nothing in this sequence-to-sequence models or transformers is nothing but a multiplication of matrices that represent data in different formats. What's different now is that I can use billions or even trillions of parameters and as much data as I can and as much hardware as I can to improve the accuracy of my models. So once again, transformers are now the state of the art in text processing, image processing.
कौन सा मिला मैं अब दोनों को भेजा था किसने कौन कर रहा है नहीं मुझे पूछो तो नहीं सेंड टू मी आई विल फिक्स तो प्राइवेट का
I'm hearing some voices, but I don't understand what's happening. Is there a question?
Yeah, please, Professor. Please. Sorry for the inconvenience.
I think Vivek has a question.
Yes, Eric, actually, I had a question when you were talking about sequential data. So I have two questions from that. I'm too beginner in this, so that's why I apologize for my basic question. So first question is, I want to know, can you help me understand what do you mean by sequential data? That is the first question. And second, is it a conscious decision when you were talking about that weather and pizza illustration, that thing? So was it a conscious decision of why you have used weather matrix for back propagation? Why not as another input in that neural network?
Okay, so thanks for the question. So the way transformers are used today, or maybe it's more it's better understood here for the sequence-to-sequence model. People started looking at sequences. Why? Because they wanted to do natural language processing, text processing, which word comes before another, and this is what then later on led to large language models. So here in this example for the recurrent neural network, I use this as a sequence. My sequence is this. So if I cook pizza on Monday, then on Tuesday I cook burger, then I cook sushi, and then starts again. So I came up with this example to ground the example somewhere, to also to make you guys understand that I can potentially model any sequence. Today, when we talk about generative AI, and we're mostly talking about large language model text, but for a large language model or in general for a transformer, working with text or working with other things makes no difference. What's happening in there is that they're encoding a specific sequence. It can be a sequence of foods, a sequence of letters, a sequence of characters, a sequence of whatever. So in the same way as you can do a sequence-to-sequence model with these foods, you can do for words. And here, I'm not sure I understand your second question. It was again just an example. So I want to. Before I only had this person cooking a certain kind of food if it rains or if it's sunny, and here I have the same situation. So there are some conditions, but there's also the sequence to keep in mind. So here is if it's sunny, I cook the same as yesterday, and if it's not, I go to the next dish. So this was just an example to tell you that recurrent neural networks came about to be able to model a bit more complex problems when you don't just have to do classification or if-then situations like we had before, but you have also a sequence to take care of. I don't know if that answered your questions.
Okay, and so following this, I had my second question that was it a conscious decision of yours in this example of using weather matrix not as another input to your neural network, but using it in a back propagation to improve your weights, I guess?
Okay. Yeah. It could have been done in a different way. So here I'm using this as a feedback loop, as an internal condition, but I could also build a model where I have the two inputs. Yes. It was just for the
Yeah,
sake
that
of
was my
giving
question.
this example. Yeah. Yeah, don't get too fixated on this example. Anyway, today we don't really use recurrent neural networks that much anymore. But what's important here, once again, is that we still have to use those vectors that we came up with before to represent the weather and the food, and then the recurrent neural network, all it's doing is multiplication of matrices to take into account both conditions and sequencing.
Okay, I understood that. Thanks.
Yeah, thanks for your questions. It's good that we clarify these things. So here, all I wanted to do in this lecture is to give you a bit of history of how we came about to use transformers. So actually, I'm not going to talk much about the technicalities behind transformers. You can look those up if you have time. But yeah, I want to reinstate, as I said before, that the biggest novelty about the transformers is that actually they can be parallelized. So what's powerful about transformers is that they can look at different, let's say they can look at the data from different points of view, and they can do it all in parallel, all at the same time. So for example, if I were to compare myself to one of you guys, then we could look at each other from so many multiple time points of view, like age, cultural background, and whatever, all the things that make us humans, if you want. And a transformer would be able to do that all at the same time, all in parallel. Look at all these nuances, all these differences, all these classification problems from different points of view, all at the same times. So that's what makes transformers really powerful. And once again, I'm not going to talk about the technicalities, but I still want to mention three key novelties introduced by transformers, besides the fact that, as I mentioned, they can be parallelized, is that they use positional encodings to do what the sequence model was trying to do in decoder-only fashion. So what is positional encodings? For each document, we save not only the frequency of how many times a specific word appeared, but also where exactly in that document it appeared. So this is actually also a very old concept in NLP and information retrieval. And it's just giving numbers to each word in a document. So for example, here, document 2 will start with the word fools, and then I can't find the number 2, but these vectors here are encoding not only in which of my document each word appears, but also which position inside the document. So this is very fine-grained encoding of where each word is. And why do I need this? Exactly because I need to encode context. So before, with convolutional neural network, I was using this sliding window that goes through the sentence and only look at words that appear before and after. Now I'm just saving all the position of all the words in all the documents, and then use what? Then use attention. Attention mechanism is a very important and powerful concept that was actually introduced with the first paper on transformers. The title was Attention is All You Need. Very cool title. And what is attention is a mechanism that is inspired by human attention. It doesn't really work like human attention, but the takeaway here is that the key point is that I can focus on different parts of the sentence based on what I learned from my training data. So when I encounter specific situations where, like the cat sat on something, I can use attention to focus on that specific part of the data to better guess what comes next, or what or how to perform classification. On top of these, I can also do self-attention, which is using the same kind of mechanism within the sentence itself. So this can be useful, for example, to resolve pronouns. We'll talk about this in next lecture when we'll talk about anaphora resolution. Every time I find a pronoun in a sentence like it or them or they, then I have to resolve this ambiguity, and self-attention helps me to do that. So in this course, because we don't have so many hours together, we are not going so much into the details, or maybe you can do that during the tutorials, but here I put some useful links of and some nice video lectures from Stanford that you can watch when you have time, if you want to learn more about deep learning architecture. And then what we use for NLP to develop NLP techniques based on transformers architecture, you can use spaCy or Hugging Face. So actually, that's the end of lecture 2 already. There are any questions? So I hope that, again, many of you already knew what is a transformer, but I think it's useful to also go over these topics for those who never seen a transformers before. And once again, it's not like you have to learn how to build the transformers from scratch. You can take the ones from spaCy and Hugging Face and try to see how you can train one of these models, and most importantly, interpret the results, because ultimately what companies are looking for in an AI expert is how to interpret results of an AI model, what to do if things go wrong. You could think of doing an ablation study, some error analysis, but if you don't know how to interpret the results, then and that can be problematic. I see someone raising a hand. Ravi?
Good afternoon. So yeah, exactly. So I have a question regarding the machine learning. Yeah, the machine translation. Yeah, I'm too beginner in this field. So like I have a question regarding being a linguistic. So how could I just just relate with this the machine translation? Could you just tell me a little bit about the machine translation, being a linguistic, because I'm not a technical background. I know German and English and Hindi. So then how this would just help me in developing my career.
Yes, many thanks for your question, because that's something that I always say, and I will also say again in the next lecture, is that we computer science are too obsessed with computer science things. So now with large language models, everybody is just working on increasing the accuracy of some machine learning architectures and forgetting the decades of literature in linguistics that are still very important. So in next lecture, I'm going to talk about the importance of multidisciplinarity, and linguistics are definitely one good example for that. You can, as a linguist, you definitely have to learn a bit about what you can do with AI, but there's still many things that a linguist can do, because it's not just about sequencing words and letters. There's so much more there. For example, what we are doing in the context of sentiment analysis when we work in multilingual settings is also going beyond the syntactic representation of text. We want to encode common sense reasoning, cultural background, some common sense knowledge representation and reasoning that should go hand in hand with a sequence to sequence model or a large language model that helps you doing machine translation. So I believe there's still a lot to be done, and together with linguists and computer science and large language models alone cannot do that. So you have you
Yeah,
have
thanks.
you have what you know, and your expertise in linguistics is definitely useful, but you need to also learn a bit about these tools so that like the ideal situation would be to work with an AI expert. So you can either work together with an AI expert to uh, use some of the linguistics models or knowledge representation to increase the accuracy or interpretability of the AI model, or you can also try to learn a bit of AI yourself and then do that on your own. But definitely there's still a lot to be done together in terms of multidisciplinary research. So later, you can contact me and we can see also how we can collaborate. I have several joint papers with some linguists, especially in different languages. And the most recent one was with the collaborator from Vietnam. So we looked at how we can use knowledge representation of Vietnamese common sense together with a natural language processing technique to increase both accuracy and interpretability of the model.
Sure, sir. Thank you so much. Yeah.
If you have time, you can take a look at these video lectures as well. I don't know if maybe they are a bit advanced for you, but yeah, I put some of the materials, some links also at the end of the previous lectures that you can take a look at.
Yeah, surely I'll go through it, sir.
I think Vivek has another question.
And thank you for that insightful talk, Professor. Because we have a time, that's why I'm asking this question. Otherwise, I would have
Yes,
not.
please. You can ask as many questions as you want. I actually like to get questions, so please ask more.
Okay, so thank you so much. I wanted to know, generally, when we talk about transformer, we say transformer is an architecture, it's an architecture, it's an architecture. So in the current space of research, is it like people are doing domain specific research on the transformer because the transformer has already reached its saturation point in terms of its own research, or is it something else people are doing with the transformer?
Yeah, so there's two camps of people working on AI, those who focus on increasing the accuracy or the interpretability of models like transformers, and those who use it in a more domain specific or application specific setting. So now definitely the core research on transformer is a bit saturated. I agree on that. So the most recent papers are more like applications of transformers, but there are also people that look at how to increase, for example, the accuracy. Accuracy actually is very saturated, but it depends also on what you are trying to improve there, because until recently, accuracy is all people cared about. Then DeepSeek came and people started looking at other things, other optimization techniques. How can I use less hardware? How can I have more interpretability? How can I have better explanation? So now the research that has been done on transformers is mostly looking at all these different facets of what it means to have a good AI model. So again, very fair question, because things have changed just recently. After DeepSeek came out, people finally started looking at other things beyond accuracy. In my group, we also had small works before that were looking at this. We have a work on so-called hardware-aware dialogue systems, in which we were building a chatbot like ChatGPT, but trying to save as much hardware as possible instead of using as much GPU as possible. And then there was also a work on hardware software co-design, again for dialogue systems. And this is something that going forward, I think it will become popular again. So it's not just about the architecture and how much we can squeeze from the architecture in terms of accuracy, but also in terms of optimization, using less energy, using less space, using less hardware, having more interpretability, having better explanations. So still a lot of work to be done in this context. But in terms of the architecture itself, I don't think there's much more to change there. I think it will be more about integrating this architecture with other techniques, like we'll talk about later in lecture 5 when we talk about neurosymbolic AI. It's about using this kind of architectures together with an external knowledge representation that can help in situations like hallucination, for example.
Thanks. That was a complete answer for me. And if you could elaborate, that when we talk about machine learning, deep learning, and transformers, if I talk about these three verticals, how is the research scenario for other two? Like, is there anything left in those two parts, or we are done with that.
Which are the two parts?
Machine learning, the first one, research scope in machine learning areas, research scope in deep learning areas.
Again, it depends on how you define machine learning. If you define machine learning as I just did when I was talking about the difference in terminology, I don't think there's much more to be done in machine learning. But when it comes to deep learning, yes, there's still a lot to be done in terms of again trying to build something that is not just accurate but can also be cost saving and hardware saving. But most importantly, what's more interesting that will happen in the future is also how to fuse together different architecture that do different things. So, for example, now the whole world is so excited about large language models, but then they are just language models. The real power of AI will come about when we can have agents that can actually do things. So if I have a large language model, and I can tell it to do something, it will actually do something for me. Now, all these large language models are trained for plausibility, to give you a plausible answer. There's no fact checking, there is no actual action coming out of that. So, real interesting AI applications will happen when we start putting many of these architectures together. And I also don't think that transformers will be the state of the art for deep learning forever. I don't have the crystal ball, so I don't know what will come next, but there are some other interesting architecture that have been proposed in the past and they could come popular again. For example, Geoffrey Hinton, before he became Nobel Prize, he also was working on this network called Capsule Network. And that was very interesting, I think, for the way it was actually encoding meaning. But then it was kind of forgotten with transformers. But you never know. As we said, also in the case of convolutional neural network, they've been forgotten for 30 years and they've been used again. So you never know what can happen next. Maybe there will be a completely new architecture coming from, inspired by neuroscience, or maybe it will be some old technique like capsule network or something else that can now be used in a different setting and have better results. Personally, now what we're working on is a neurosymbolic AI. So we are using transformers and other architecture by trying to also minimize the power consumption and hardware usage together with external knowledge bases that can be useful for integrating knowledge that, for example, is not in the training data, or to integrate knowledge that by definition is not in the training data, like common sense knowledge, because some common sense knowledge, the very basic pieces of common sense knowledge, are so trivial for us humans that we don't write those down in documents. So supposedly large language models do not have access to most of it. So that's something that I think will also be popular moving forward. But I'll talk more about this in lecture 5. I see there's another question by Sunil.
I'm grateful for your answer. Thanks.
Thank you.
Yes, Eric. Thank you. Thank you for your informative lectures. Actually, I have two general questions. One is that recently this DeepSeek have been started last 2 months, 3 months, and how it is different infrastructure point of view. Let's say if you are using that ChatGPT, Gemini, and all, they are required lots of GPUs, which is required cooling and electrical things and all. Because I'm coming from the ELV field, I'm making the data center. So because of the DeepSeek, is this going to change the scenario? Because many companies talking about a huge data center before DeepSeek. Now, little bit they are thinking, okay, shall we do or not? So, what do you think? What is your input on that?
Yeah, thanks. This is also something very important that I haven't discussed before. So, at the beginning of this lecture, I said that we also have to look at other disciplines like also social implications of AI. What I didn't talk about is politics as well, but also the financial markets. So, what you realized the moment DeepSeek came out, for example, a lot of AI company value went down because people thought, okay, I can build a large language model spending so much less money than what OpenAI did. And that's partly true. Then there are things to discuss in terms of how DeepSeek was built, because if they really used ChatGPT just kind of distill knowledge into DeepSeek is a bit tricky. But then you also see other phenomena after that. So many governments started coming up with things like, oh, okay, DeepSeek is dangerous because China is going to steal your personal information. So many countries even ban DeepSeek. And I think that's wrong because I don't think anything is happening there. But ultimately, I think the fact that DeepSeek came about is great because it showed us that we have an alternative way to build these models, and that can even be like running on your computer. But then I don't think that this will affect in the long run companies like OpenAI, because OpenAI, with all the budget that they have, will continue to innovate. China will also keep doing the same, but there are two different kinds of perspective to the problem. So ChatGPT is focusing more on accuracy, and they are doing a lot to increase also fact checking and removing hallucination, while DeepSeek is more focusing on saving costs and hardware. But also, if you look at the user experience, it seems that because of the training mostly, ChatGPT seems to be much better to give you recommendations about things that are in the US or in the Western world. Like if you ask for recommendations about food and restaurant, it will give you a lot of detailed information, but not for restaurants in China, and vice versa. The users of DeepSeek find out that DeepSeek can give you very fine-grained information about restaurants in China, and not so much about the ones in US. So maybe in the long run, there will be just two divided by cultural differences. I don't know, but to me now the biggest difference is that ChatGPT is focusing on accuracy, while DeepSeek is trying to do the same with a bit less accuracy, but also by spending much less, and most importantly, occupying less space, less hardware, less energy consumption, which can be key for some applications where you don't have the luxury of having so much space. So I think there are two interesting take on where the market is going, but I don't see them mutually exclusive. I don't think that in 5 years from now, one of these two will disappear. I think they will go in parallel, and maybe many more will come about as well.
Yeah. I think that there will be many more, maybe LLM will come. Like India also announced within 1 year they have their own.
Great.
So
Yeah,
if
we are so.
it is many will be there, and everybody will be using kind of localized data. Okay.
Yeah, that's what we need, because as we were saying earlier, it's not just about the different language, it's also about the specific cultural background, the culture specific common sense, and also the location specific details that you can only have with the data from that specific area, country, and culture. So yeah, many many avenues for building new and useful AI models. We ourselves in my lab are now building our own large language model for effective computing tasks. So this will not be just for sentiment analysis, but anything related to emotions, so that even applications like depression detection, suicidal ideation detection, or personality detection, anything related to emotion could be done more effectively with this large language model.
Good. Thank you, Eric.
No problem. I see another question from Ranjan. I can't hear you. Are you unmuted?
Am I audible, sir?
Yes, you are.
So my question is, how do you see LLMs evolving over in future actually, right? So ultimately, what we are going to achieve with the AI is like we want to go towards artificial general intelligence, right? Do you see LLMs solving the problems of artificial general intelligence in future? And if not, then what needs to be done? Especially, what is there which is like lagging in when it comes to LLM, and why it can't solve each? Is it some? What is it which we can do better, so that we can reach towards the AGI thing actually, right?
Thanks for your question. This is actually what the next lecture is all about. So I'm going to talk about large language models and what are their limitations. So now the biggest limitations is that they are language models. They can't actually do anything. So the one thing that many businesses started doing is to put large language models everywhere. So now, even when I want to do something for my bank account, I'm chatting with the chatbot, and then the large language model is trained for plausibility to give you a plausible answer. So you always left with this doubt on whether what you're given is something that you can trust, and if this language model is actually doing something. Because if I'm talking to a chatbot and I ask the chatbot to do some kind of transfer movement on my bank account, and it tells me yes, I've done it, who tells me that this answer is just generated or it's actually being done? So the next step, the next stage of AI is where, together with these large language models and other techniques like neurosymbolic AI that we can couple large language models with to make sure that do not hallucinate, is also some doers, some other models that are not just language models, but they do things. So this is also goes under the name of agentic AI, using agents. But it's not just about what to do with that. It's also a question of how truly intelligent large language models are. And no matter how good they'll become, and this is also something that I'll talk about later, there will still be an intelligence that is very different from us. So we are biological intelligences, and we will always be different from machine intelligence. So no matter how good a large language model will become, even 10 years from now, it will never truly know the meaning of pain, pleasure, or even emotions. So you can say that one day large language models will be as intelligent as us if you discount the fact that there are different kinds of intelligence. So yeah, some people say that AGI is possible. Some people say that it's impossible. It depends once again on how you define intelligence and what for. And this opens up philosophical questions about what is the meaning of AI and what is the meaning of humanity as well. Some people are saying that Our goal as humanity is to create this AI that then will be much better than us because it will not be biological. It can live on any planet. It can live forever. It can maybe self-repair or self-replicate. But then again, what is the meaning of this? Why do we care? What do we create this AGI for? So these are very much philosophical questions that I think will need time to answer, together with many other questions that I will ask later, like, are we humans even a good model for building AI, and how much should AI feel, and so on. But in short, the answer to your question is that we need to go beyond what a large language model does. For now, a large language model is something just that is trained for plausibility, to give you a plausible answer given a question, but it needs to be doing much more than that. It needs to be explainable, it needs to be interpretable, it needs to be doing fact checking, and most importantly, it needs to be able to actually do things for you, not just give you answers. And last but not least, it also needs to be personalized, given your specific cultural background and personality and personal preferences. So another avenue that many are working on right now is personalized AI. And this is also something that I'll talk later in the last lecture, I think. But then, yeah, your question is very much relevant because it's exactly what we're going to talk about later.
Thank you, sir. Like, what in particular LLMs, right? So, can LLMs like um, mm, uh, does it solve? Can it solve the problems of reasoning actually? Uh, do you think that in near future it can solve the problems of reasoning when it comes to LLM?
So people have already started working on how to increase what the LLM can do, and something where you can already see in LLM is that they can now access the internet to find information that maybe they don't have in their training data set. But in terms of reasoning, actually, it also depends what kind of reasoning. So some LLMs are using tricks so that when you, for example, ask a question that is very much about common sense, they do not use this usual system of that they use for question answering or information retrieval. They switch to a specific system for common sense reasoning. So, but these things needs to be built, kind of be handcrafted. So this requires time. That's why I say that as we move forward, LLMs will become better and better. This is already happening. There are some specific questions about common sense, and the system needs to be switching to a different kind of reasoning. LLM per se is only good for doing specific kinds of reasoning that are mostly related to question answering, information retrieval. When you start asking questions about, for example, common sense, spatial common sense, like you start telling a story like, I passed this object to this friend go to the living room, this friend falls, and then in the end you ask, where is this object? So these kind of questions that require more commonsensical reasoning need to be done using a different system. But that's exactly why I believe that the future of AI is neurosymbolic. So you have large language model as a sort of system one, and then you have something else like a knowledge base as a system two, and you can switch in between these two or have these two systems help each other depending on what kind of reasoning is required. And this is also very much cognitive inspired because we also do the same. We have that's what people talk about when they talk about left brain versus right brain, or slow thinking versus fast thinking. So I think with LLM, we have done an amazing job at replicating that kind of fast thinking, that some sort of intuition that you can already blurb out given your past experience, but then you also need to implement the slow thinking part, the part where you switch to a different kind of reasoning, which is not optimized for plausibility, but for something different, where you are actually replicating or simulating something in a virtual environment. Because if I tell you a story, you start visualizing that as a little movie in your head. If I tell you like a narrative like the one before, but that's not what a large language model does. That's the biggest limitation of large language models. They just used probabilities in a very efficient and smart manner to give you an answer. But the way we should do it, especially for specific question, is that we have to again simulate that kind of reality and then give an answer based on that, not on some calculated probability.
Thank you for your answer, sir. I find them very yeah.
Thanks. This is also very relevant to what we're going to see later, because lecture 5 is also about this. I will also talk about system 1, system 2, and neurosymbolic AI.
I'll be waiting for them, sir.
So I don't know what's the schedule now. Oh, is there another question? No. Should I proceed or are we done? As if, should I continue or leave this for tomorrow?
Hello, sir. The session is done for today.
Okay, great.
Yeah. So we can continue about this lecture 3 or tomorrow.
Okay. Okay, so thanks for your attention. If you have more questions, you can contact me later or also ask questions tomorrow. Enjoy the tutorials and see you guys tomorrow. Bye-bye.
Thank you.
Thank you.